Good evening, everyone. This is the 16th year of the Silicon Valley Astronomy Lecture Series. My name is Andrew Fracknoy. I'm the astronomy professor here at Foothill College in Los Altos Hills, California. And it's really great for me to welcome everyone here in the Smithwick Theater and everyone watching us or listening to us on the World Wide Web to this very exciting lecture in our Silicon Valley Astronomy Lecture Series. This series is underwritten by four very good organizations: the Astronomical Society of the Pacific, NASA's Ames Research Center, the SETI Institute, and then the Foothill College Astronomy Program. Those of you in the room have information about them on your program, and everyone else, I hope you'll look them up on the web. Tonight's lecture is a very exciting topic. It's entitled Innumerable Globes Like This One, Searching for Life Beyond Our Solar System. This is one of the most interesting areas and productive areas in astronomy, and we're delighted to have Dr. Tori Hoehler with us. He is a research scientist in the Space Sciences and Astrobiology Division of NASA's Ames Research Center. He has worked as part of the Curiosity rover science team, which is exploring Mars right now, and on the science planning team for NASA's new Europa multiple flyby mission. Europa is a satellite, a moon of Jupiter's, which we're very excited to explore from a biological point of view. He is a Kavli Frontier of Science Fellow, a Fellow of the California Academy of Sciences, and was the American Geophysical Union's 2009 Carl Sagan Lecturer. In addition, he just told me that he won the NASA Exceptional Achievement Award, the medal that they give, in 2015. So we're happy to see his being rewarded by all these great organizations and his still making time to be with us. It's a real pleasure for me to introduce to you Dr. Tori Hoehler.
Well, thank you all very much for coming. As Andy mentioned, I'm local, and I love living in a community that values science. And I have to say, I've really been looking forward to this. It's been fun to think about how to make this topic come alive for you guys. And I hope that I can convey some of the excitement, some of the sense of possibility, and also some of the challenges that exist in this field. So with that said, and now that the exits have been firmly bolted shut and escape is impossible, I will share with you something potentially embarrassing. And that is that although this is an astronomy lecture series, I am actually not an astronomer. Oh, I know. You know, we all have our shortcomings, and I try to be a productive member of society anyway. And actually, now that I'm opening up to you, although this is a talk about life, I'm not a biologist either. And so you may be wondering what kind of terrible bait and switch you've fallen prey to. What I am actually is a chemist, and what I hope you'll see over the course of the next 3-4 hours or so, maybe not quite that long, is that this is an endeavor that will not be purely an astronomical one nor purely a biological one. It will ultimately require the inputs of geophysicists and geochemists and biologists and astronomers. And all of those things converge to me on chemistry. That is a language held in common among all of them. And I hope that you'll see by the end why we need those things and why chemistry is the language in common. So this question, are we alone in the universe, is by no means a new one. And in fact, my title here, Innumerable Globes Like This One, actually, before I do this, I put these folks up here on the title slide so I wouldn't forget to thank them, and I actually just did. In the spirit, having said that you know, this is an endeavor that requires many people, I actually reached out to many friends and colleagues of mine for materials to try to help really make this stuff tangible. So Natalie Battaglia is the mission scientist for Kepler that has given us so many of these exoplanet discoveries. She and the entire Kepler team really do a fantastic job of visualizing their data and making it tangible to people. And a lot of what you'll see about where we are now comes from Natalie. Jeremy Kasdan is helping to design the next generation of telescopes that will actually let us go after this question of whether life is out there. Scott Sanford and Nikki Peranto are colleagues of mine at Ames who gave me some of the chemistry data that I will torture you with later. And Vicki Meadows and the Virtual Planetary Lab. So Virtual Planetary Lab is a group that I'm part of that really has dedicated itself to understanding the scientific context that surrounds the search for life on exoplanets. That group, led by Vicki Meadows, has really been kind of leading the way in understanding how we go after exoplanets, and I'm pleased to be a part of that. So this title, Innumerable Globes, like this one, references a 4 centuries old text from this person, Giordano Bruno. He was a Dominican friar. And I'll read to you a few lines of this text because I think that it's really remarkably foresightful. But before I do, I want to provide a little bit of context. So this was written in 1584. That's about 40 years after Copernicus told the world that, in fact, the Earth revolved around the sun and not the other way around. It still was very contentious at Bruno's time, but it was in people's minds. But it was still a good 25 years before Galileo first pointed a telescope at the heavens. So at the time he wrote this, no one had actually seen a planet through a telescope. They simply were points of light in the sky that behaved a little bit differently than the stars did. So with that in mind, think about what Bruno wrote. He said, "There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. We see only the suns because they're the largest bodies and are luminous, but their planets remain invisible to us because they're smaller and non-luminous. The countless worlds in the universe are no worse and no less inhabited than our Earth." So what is unique about this moment in time is not the question we're asking, it's the potential to actually answer it in a scientific way. And that's what I'll try to tell you about. So what about this notion that there are countless suns and countless Earths? In fact, we have begun to count. We know that our galaxy alone is host to about 300 billion stars. And the observable universe is maybe 70 billion trillion stars. That's a lot of real estate out there, right? There must be someone. So we also have begun to count the planets as of about a quarter century ago. And what I want you to watch is the pace of discovery. So this is a little bar graph that shows you in cumulative numbers the exoplanets that have been detected beginning in 1989, and watch how this takes off. And what you can see actually, so you can see different methods of exoplanet discovery. There are about half a dozen of them overall that have been brought to bear on this problem, and 2 of them really dominate. There's the red one down here and the green one up here. And I'll tell you a little bit about those. In fact, I'm going to tell you mostly about one of them, and that is Kepler. So as of now, at the end of 2015, we know about almost 2,000 confirmed planets. There are several thousand more that are strongly suspected to be exoplanets. When I got to Ames 17 years ago, there were 2. Right? It's amazing the pace of discovery. So how do we find these things? This is how Kepler finds exoplanets. This is our sun, and this is the planet Venus right up here. And every once in a while, the planet Venus, or the planet Mercury, or Earth for that matter, transits across the face of the planet. And this is actually something you can see. Maybe some of you have seen it. If you look with the right kind of glasses that protect your eyes, you can actually see the little dot of Mercury or Venus moving across the sun's face. But what if you actually didn't get to see the sun as a disk? What if you only saw it as a point of light? Then what you would rely on to know that there was a planet there is not seeing it with your own eyes, but watching the sun dim just a tiny little bit. And the area of this little shadow compared to the area of the sun overall is about 1/10,000th. That's how sensitive you need to be to the dimming of the star. And this is what Kepler actually does. It sits and stares at the stars, and it watches. And every once in a while, as the planet moves across the star, you can see that the amount of light it sees drops just a little bit, and it stays low. And when the planet continues or completes its transit, the light field comes back up. And you see that once, and it's interesting, and you see it twice, and you get pretty curious, and if you see it 3 times, you can be pretty convinced that maybe that's a planet. Right? And that's actually what they do. They watch for 3 consecutive transits. So what you can imagine actually is that your sensitivity to planets like this depends on how often they transit. If it happens once every handful of days, awesome, right? Look for 2 weeks and you could actually see several transits enough to say there's a planet. If it happens once every year, as it would if you were looking at Earth against the sun, you'd have to wait for 3 or 4 years to convince yourself that what you'd seen is a planet. As well, it really matters what size planet you're looking at. If you saw something that was like this size, right, moving against the sun, that's a big dimming of light and it's easy to see. If you're looking for a diminishment of light of 1 part in 10,000, right, that's not easy to see, especially if the sun has variability and things are going on. So I want to show you the same data that I showed you before, the number of exoplanets discovered through time, but in a slightly different way. So here on this axis is the orbital period, how long it takes the planet to go around the star. Earth is here, right? And I circled where Earth would be in red. And on this axis is how big the planet is. So this is 1 times Earth radius, 4 times, and 10. And watch the pattern of how this plot gets filled in as the years go by. So initially, all this stuff is up here. These are planets that are very, very big. Everything up here is bigger than Jupiter, right? And close in. So relatively short orbital periods. Those are the things that are easiest to discover, right? And here's where we stand as of 2015. Although it seems like maybe I have forgotten something. That's what Kepler has given us, right? Amazing. And here's Earth, and now what you notice is these exoplanet discoveries are beginning to push out in this direction, longer periods, and down in this direction, smaller planets. And there are a couple that are even right in the neighborhood of Earth. And so this starts to get interesting. And we have enough discoveries that we can actually look at this in kind of a statistical way. So here's a plot of planet size. If Earth is 1, so Earth would fall into this bin, then these are planets that are from about 1.5 to 2 times the radius of Earth, and up from there. This is the number of planets per star. So saying there's 0.3 planets per star is like saying you have 2.5 kids. It doesn't actually happen that way, right? But it's an average, a statistical average. And there are a few things that you can take home from this, right? The first is, here in the bin that has Earth, 1 to 1.4 Earth radii, and here, 1.4 to 2, if you add those two up, basically it means that every other planet, every other star has a planet about the size of Earth, right? That's kind of amazing. There are lots and lots of planets out there. And there's some other cool stuff, right? Kepler, its mission has been to look for habitable planets, but it has been this absolute treasure trove of data about exoplanets. This stuff that you see here, these gray sizes, we don't have anything like that in our solar system. So all of the rocky planets, our solar system kind of falls nicely into 2 categories, right? There's all the stuff in the inner solar system that are rocky planets like Mercury, Venus, Earth, Mars, and then everything in the outer solar system that's big and gassy and icy and so forth. So that's here and out here. And we don't have anything that looks like this in between. What are those guys, right? Still trying to figure that out. But as we've crowded in on this part of the plot, as we've gotten to smaller and smaller planets, a few years ago, we started getting stuff like this, right? This is actually taken from the press release. NASA's Kepler discovers first Earth-sized planet in the habitable zone of another star. So what is the habitable zone anyway, and why go to the trouble of wording it in this very particular way? Why not just say, NASA discovers habitable planet? No, NASA discovers first Earth-sized planet in the habitable zone of another star. So what is the habitable zone? This is this idea, sometimes referred to as the Goldilocks Zone, that there's a distance away from the star that is just right for life. And what just right means in this case is that the temperature at the surface is right for liquid water. Right? Water can exist in a liquid form at the surface. And the idea is if there's a blazing hot sun over there, and I walk this way, which I promised I wouldn't do too much, and I walk this way, I get hotter because I'm closer to that star. And I go this way, and I get a little bit cooler because I'm farther away from the star. And in the middle, I'm just right, and I can have water at the surface. And you see several things represented here. So on the bottom, this is the radius of the orbit of the planet where Earth is 1, so there's Earth right there. But then you see this funny thing over here, right? What are these? There's this little red guy, there's this sort of giant white guy. Stars, of course, come in different shapes and sizes. Some of them are smaller and cooler and dimmer. Some of them are larger and burn much brighter and hotter. And so the distance that is right for the planet to be away in order for water to be liquid varies depending on the kind of star that planet is orbiting. Here, the planet can be very close in. If it's something like our own sun, it's a middle distance, and as you get to bigger, brighter stars, it would have to move outward. So this idea of the habitable zone sometimes gets some flack from people, right? So Andy told you I'm involved in planning this mission to Europa, which is, way out here outside the habitable zone. But the interest in that mission is understanding whether Europa is habitable and, in fact, inhabited. Right? So why this notion of the habitable zone when we know for sure there can be places outside it that are habitable? The point is that it becomes important to think about places where water is liquid on the surface, because we are not trying with this diagram to say where life is possible. We're trying instead to say where we could detect it. And I'll try to come back to that point a little bit later on. That's the reason for having the habitable zone idea. Where do you look to have a chance of detecting life? So what can we say right now based on things we can actually observe? And what can't we say? Well, we can say a lot about the star because we see the star. We see its light. We can say how far away it is, what size it is, how big, what type of star. That tells us something about its light spectrum. We can even tell the age of the star. And knowing something about the age of the star, we know enough about the physics of stars and their evolution that we can say something about its history. Right? Was it tempestuous in its youth? Did it cause problems for any planets orbiting? So we actually can say a lot about the star. But what about the planet, right? That's down here. Remember, you don't get this big spatial view that shows you the planet as a disk. All you get is a tiny little point of light that you see periodically dimming. So what can we say? Well, we can say something about the orbital period, and that lets us know how far away it is. So we do know how far from the star these planets that we're finding are. And what's cool is there are these two main methods of finding stars. There's the Kepler method that I showed you. There's another one called radial velocity. It also gives the orbital period, but instead of saying how big the disk is, it actually tells you something about how massive the planet is. And if we know those two things, we can make a statement about density. So if we have both of these working in concert, we can make a statement about density, and that at least gives us some constraint on what the planet might be made of in bulk, right? Is it mostly metal? Is it metal and rock like we are? Is there a lot of water or gas or whatever? So this allows us to actually constrain something about the planet without actually seeing it or visualizing it. What don't we know based on what we can do right now? We don't know anything about the surface or atmosphere composition because we can't actually see it. All we're looking at is a shadow. And I put a little asterisk here because that's not entirely true. There are a few planets out there for which we've actually been able to do this. It's just they're not the ones that are interesting to us from the perspective of looking for life. So if we don't know anything about that composition, we don't know, for example, whether or how much water is there. Right? If there's no water there to begin with, it really doesn't matter whether the planet is close enough to the sun for water to be liquid. There's just no water. We don't know anything about whether there might be greenhouse gases in the atmosphere. Whether there are ingredients for life. We don't know how reflective that planet might be. Why mention this, by the way? Why mention, who cares how reflective the planet is or if there are greenhouse gases in there? This is the reason, right? What we really want is a statement about the temperature at the surface of the planet. The idea of the habitable zone is that we're trying to say, if there's water there, would it be in the liquid form? Are there oceans and lakes, or is the entire thing completely frozen over as a ball of ice? So what determines that? If we ask that question for our own Earth, it's a couple of things. So the main one that we just talked about is how much energy is received from the star, right? How close is the planet to the star? How much energy is it getting? But we know that if we can see the planet at all, we look up in the sky and we see Venus as a morning star or an evening star or Jupiter, things like that, some of that sunlight is getting reflected away, right? So it matters not only how much energy is received, but also how much is reflected back out into space. That's energy that the planet absorbs. And then, as the planet heats up, it radiates some of its energy back out to space. So it matters how much the planet radiates out to space, and we know from our own planet that we have a greenhouse effect, which is like a blanket that serves to hold in some of that heat. All of those things collectively are what determine the surface temperature of our planet. They're what control whether water is liquid or not here on Earth. And which of these things can we know about for exoplanets based on what we can actually observe now? Only this one. right? We don't know about the others. We don't know how much is reflected back out to space because we don't know how reflective the planets are. We have no idea about greenhouse gases in the atmosphere or about the radiant energy of the planet. And that's why we're careful about these statements. That's why we say that the planet is in the habitable zone, right? We think it's in an area where the conditions might be right to keep water liquid at the surface, but we don't know for sure. And just to give some perspective on these numbers, I mean, maybe these are throwaways, right? Who cares, how reflective the planet is or how much greenhouse there is? We can actually look to our own solar system for some sense of perspective. We need to look no further than Earth, Venus, and Mars. So the main parameter that we talked about, how close to the sun are you, how close to the campfire, right, is how much sunlight are you getting? So if we think of the Earth as 1, Venus gets almost twice as much because it orbits much closer in. Mars, I think I've lost my laser pointer. Mars gets only about half as much light, right? So, that tells you something about the planets, but then if you look at how reflective they are, Earth reflects away about 30% of its light, Venus more than twice as much. So actually the amount of sunlight that Venus actually absorbs is less than we get here on Earth, despite the fact that it's closer. Okay? Mars reflects much less of its light, and so it absorbs a reasonable amount of sunlight as well. But what really explains the temperature of these planets is the amount of greenhouse warming. And this is actually instructive to look at, right? So Earth has a natural greenhouse, even exclusive of what we're doing, pumping carbon dioxide into the atmosphere. Earth has a natural greenhouse that comes mostly from water vapor in the atmosphere, and it gives us about 33, 34 degrees centigrade of extra warmth that we wouldn't have otherwise. Venus has the same thing, but it has an atmosphere that is 90 times as big as our own and made almost entirely of carbon dioxide. That's worth a greenhouse effect of more than 500 degrees Celsius. That world is scorching hot at the surface. And Mars has an extremely thin atmosphere and very little greenhouse effect, and it's cold on the surface. Water couldn't exist in a liquid form there. And I put this up only to be instructive about the fact that it matters to consider these parameters, and these are parameters that we just don't know yet because we don't have the ability to observe them. But this is what Kepler has shown us so far. This is a habitable zone seen in green here. All of these planets, I got the pointer back, so the solid blue ones, these are planets we know about and are confirmed. The yellow open circles are things we think are planet candidates, and these are planet candidates here. And actually, there are quite a few in the habitable zone. So just in the small patch of sky that Kepler has actually looked at, it's discovered quite a few planets. And here you see Venus, Earth, and Mars for reference. And some of these are actually quite close. So some of these are really pretty similar to where Earth lies in the habitable zone and pretty similar to Earth in size. So we know enough about these things. We've discovered enough of them to have sort of a statistical view of how common these habitable planets might be. And Natalie Batalha has a really great analogy for doing this. So if you think about the Milky Way galaxy, our galaxy, as scaled to about the same size as the United States, and you ask the question, how far do you have to go from this spot before you find the first Earth-sized planet in a habitable zone of its star? Right? What distance would that be? So by show of hands, who thinks we have to leave the state of California to get there? Don't be shy. You all have to raise your hand for something. Who thinks we have to go outside the Bay Area? Right? Maybe up to Lake Tahoe. It's kind of nice up there. Outside of Mountain View? So actually you could get there walking back to your car. It's about a quarter mile from here. By the time you reach the parking lot, you'd have reached the first habitable planet. Right? They're abundant, and we won't have to look very far to find them. And actually, Kepler hasn't looked in our little particular neighborhood of the galaxy, but we can use those statistics to say the first habitable planet we encounter should be about 3 parsecs. That's about 10 light years from us. And so if we look out to about 3 times that distance, okay, this is about 30 light years from us, these are all the stars within that radius of us. And statistically speaking, there should be about 25 or 30 planets within the habitable zone of their stars. Right? So this is stuff we can actually see. We actually have a potential to look out and get some answers to these questions. So let's go, right? I want to make the point, though, that looking for life beyond the solar system is a lot different than looking for life within it. And that may seem like an obvious statement, but I will try to make that point in as heavy-handed a way as I can. What can we do within our own solar system? We, as a species, over the last 5 decades or so, have sent tens of spacecraft toward Mars. We have mapped it so effectively with orbital imagery that you can tour it in Google Mars. And actually, a lot of that imagery is way better in resolution than what you find in Google Earth, for example. We have driven more than a marathon's worth of distance on the surface of Mars. We have lifted up rocks and turned them over to peek underneath. We have drilled holes in the ground and looked inside. And we have filmed ourselves doing it. This is actually a picture of the Curiosity rover right here descending on its parachute as captured by a spacecraft orbiting 250 kilometers above. That is one of the most remarkable images I've ever seen. And it shows you that even NASA is not above the occasional selfie now and then. Did any of you happen to catch the lecture last year by Carolyn Porco? Really excellent lecture last year. Some of you, I'm glad that a few of you did. So Carolyn is the imaging lead on the Cassini spacecraft that has gone to Saturn. And it was an hour full of some of the most stunning imagery I think I've ever seen. And she had to cherry pick it from among hundreds or even thousands of comparably stunning images. There are movies of storms on Saturn. There are pictures of waves in the rings. There are jets from the moon and Enceladus. Really extraordinary stuff. And that's just the imagery. The science yield from the other instruments is comparably good. And that's what you can do when you take a spacecraft the size of a school bus and load it full of cameras and capable science instruments and let it drive around the Saturn system for 12 years. Amazing what you can do when you're in your own neighborhood. But what if all you get to see is just a tiny little point of light, which actually many of you can't probably see from where you are. So what if that's all you get? A little pinprick of light, or this. Okay. Are those habitable? Is there life there? How would you know? Right? In fact, one of these is decidedly not habitable. One of these might be somewhere under the surface and maybe was in the past. And this one is not only habitable, but there's reasonable evidence that there's life there. The point is, when you're in the solar system, it's tangible. You can pick up, you can look at, you can ingest and analyze. When you're looking outside the solar system, all you get is light. But light is actually a lot, right? And actually, this picture is a modern-day cousin to what I think is an absolutely iconic image. This is what Voyager 1 saw from about 4 billion miles away as it looked back toward home. And right up here, where the arrow is, that's our planet Earth. That's what Carl Sagan called the pale blue dot, and he actually wrote quite poetically about it. But you can begin to see some of what the problem is. So it's not just a little dot hanging out by itself. It's actually kind of obscured and lost in the hazy glow or whatever that is. And it tells you part of what the problem is. Because if I look at two things on the horizon, a star and a planet, and I start to back away from them, they appear to me to get closer and closer. And ultimately, they'll be very difficult to resolve. And actually, we can visualize this. So suppose we take the Hubble Space Telescope that has given us these extraordinary images of deep space, and we bring it to bear on this problem. And we put it at a distance of Mars and ask it to look back at the Earth and Moon. It would look something like this. That's actually pretty remarkable if you think about it, right? Looking from tens of millions of miles away, and you still see this much. But what if you move it out to 20 astronomical units? That's about the orbit of Uranus. It would look like this. You can actually still see the moon a little bit, and you can resolve some of the detail on Earth. Now suppose we go 10 times farther away. Voyager 1 is about 134 astronomical units from Earth. Suppose we go out to 200. Now you see it as a faint dot, but still a pretty well-resolved dot. And now we go 100 times farther still, and you begin to see the problem creeping in. Now the planet starts to get lost a little bit in the glow of the star. And if we go 10 times farther still, So this is the distance now between us and the very nearest star, Alpha Centauri. So if we looked back at our solar system from Alpha Centauri, this is what we would see. I put a circle where Earth would be, and you can see that it's completely lost in the glare. And actually, Bruno told us that this would happen. We see only the suns. Their planets remain invisible to us. How bad is this problem? The star is about 10 billion times brighter than the planet. That's how much brighter the sun is than Earth. And if you think of the sky as representing 180 degrees from horizon to horizon, the distance between them that you would perceive is about 2/10,000th of a degree. So that's a bit of a fly in the ointment. Fortunately, the astronomers are real smart. Don't tell them I said that, because they'll get swell heads about it, but there's a little brain power that they can bring to bear on this problem. And we have engineers who can gently put down a Mini Cooper-sized rover on the surface of a planet 100 million miles away by lowering it from a hovering rocket. So they'll take care of this. And in fact, there are a couple of concepts that are in development now and that are showing real promise for this. And they both amount to kind of doing this. So the spotlight is there. If I want to see who's in the back, I put my hand up like this, right? And I block out the light. Simple. One of those happens inside the telescope. The other actually happens outside the telescope. And that's the one I'm going to show you now, because frankly, it seems more like something that comes out of a 60s era Bond movie than an actual thing. So look at this. Here's the telescope. And this thing, here's the telescope. This thing that's unfolding in space is a star shade, right? Here's the part where the evil supervillain holds the Earth ransom by blocking out the light of the sun. So watch what happens as the star shade moves in front of the star. So first there's the glaring light of the sun. We put this star shade in front of it, and we can actually resolve the planets. And what's really cool about this, so this star shade, you have to imagine something that's about half the size of a football field. It's massive, and it sits about 50,000 kilometers away from the telescope. But what's neat about that is, if you move it a few centimeters at a distance of 50,000 kilometers from the telescope, you have incredibly fine control on how you're controlling the size of that disk against the star. And a few of you may be wondering why that sort of interesting flower-looking pattern instead of just a plain disk. So it turns out that light can actually turn corners a little bit. Light kind of bends around objects. And if you put just a plain disk in front of the star, you have a problem that light bends around. So the last decade or so has been spent understanding how to construct the edges so that you eliminate that problem. Right? And in the video, what you saw is that the star disappears and you can see a Jupiter-like planet orbiting and that kind of thing. That's not how it would look in real life, of course. But if we do this right and it works the way that it's projected to work, we might actually see something like this if we looked back at our own solar system. So here's the residual light from the star, and there's Earth actually peeking out. And the astronomers would be thrilled to get an image like this, right? To have that little dot of light on which to make a discrimination, is there life on that planet or not? So what about Bruno's final prediction? The countless worlds in the universe are no worse and no less inhabited than our Earth. Is that true? If we can make these telescopes work the way we think we can, we actually may be able to address that question. And the idea behind how we're going to do it is actually very simple, right? It's so simple that we can demonstrate it here as a group. Okay? And this demonstration works best if everybody takes part, so I hope you will. Right? Here's what I want you to do. Take a breath and hold it. Okay. So, several important things just happened. The most important, from my perspective at least, is that an entire auditorium full of people was literally waiting in breathless anticipation of what I was going to say next. Thank you all for being the fuel of that little ego trip. But there are some other less narcissistic things that also happened. When you did that, you changed the composition of the atmosphere in the room. What you breathed in came out looking different, and as a result, the composition, chemically speaking, of our environment changed. And it changed in ways that alter the light that would come off of our planet, right? It's something that we could see if we looked with the right kind of eyes. You did that using an energy source that could just as well fuel life that is wildly different from our own. Energy for me is energy for anything, right? Doesn't matter. But, and I hate to be the one to break this to you, what you just did was a little bit boring from the perspective of looking for life. So this is a whole bunch of assertions that I'll try to back up for you over the next handful of slides. And really what this boils down to is we need to make our discrimination based on light, right? We need to look with the right kind of eyes and say, based on a little bit of light from the planet, is there life there? So most of you probably know what we perceive as white light from the sun is in fact composed of many different colors of light representing many wavelengths. So if you were to pass light through a prism, as did the noted English physicist Pink Floyd in their now famous Dark Side of the Moon experiments, you would find that the white light is broken into colors, right? And instead of being sort of, the several distinct colors, violet, indigo, blue and green, yellow, orange, and red, in fact, it's a whole continuum of colors. And it wouldn't matter how finely you chopped up that spectrum, you'd see that this little slice was slightly different from that little slice. And when we perceive color, so suppose that we look at a leaf, and this is a maple leaf, just in case any of you were wondering, because I'm half Canadian. Didn't want you to look at the Pink Floyd album cover and get the wrong idea about what that might be. If you look at if you look at a leaf and you see green, what's happening is this. So here's a plot of wavelength on this axis. That's what controls the color of the light we see. And I've put them here, right? So here's violet, indigo, blue, and green. This is the part of the light spectrum that we see. Okay? And what happens is the white light comes in, and when it interacts with the matter of the leaf, it changes. So a little bit of the light is absorbed here. I've lost this. So a little bit of the light is absorbed over around 700 or so. A little bit of the light is absorbed around 450 or so. That's chlorophyll doing its job. It's actually extracting energy out of the light that hits it. And what's left is mostly green, and that bounces back, and that's what we see. And the point of saying this is, we perceive color or things like that, that's actually chemical information. And if you break it down in this way, if you spread the spectrum apart and look at it in this kind of graph, that's chemical information that you can actually see. So what we perceive as color is information about molecules. And many of you probably know that what we see, the part of the electromagnetic spectrum that we see, is only a very fine sliver of it. Right? If you go way out in this direction over here to much shorter wavelengths, that's X-rays, for example, and if you go over there, there are radio waves or microwaves. So we perceive only a very fine part of that spectrum, but there's value in looking with different eyes. And I'll direct your attention to this part over here. So I've said that we see mostly green here because that's the part that bounces back to us, but look at this feature here, right? The most reflective part of the leaf is not the green part, right here, it's way out in this red light that we don't even see with our own eyes. But fortunately, there are cameras that can see. So what would we perceive if we looked at that? What would we see if we looked through different eyes? You can actually take infrared photographs. This is what we would see. The green of the leaves is gone because the single most reflective thing is that infrared light that we don't perceive with our own eyes. But it's there, and there's valuable chemical information in it. What if we look a little bit further into the infrared? If we could see through different eyes, we would see that we all glow with our own light. Isn't that a nice thought? All of us are glowing with our own light. Of course, everything else is too. Anything that has a temperature greater than 0 is glowing. But it's information, right? There's energy coming out. There's a potential for energy to be extracted. And if we see the interaction of matter with those wavelengths of light, we can make some interesting statements about what's there. So the experiment we just did, I made the claim that you breathed in, you changed the chemical composition of the room around you. So how would we actually see that? Now that we know, we can see information by looking at the light. So this is exactly the same kind of plot that I just showed you. It's wavelength here, only now we're looking way out into the infrared. Okay? And here is how much light shines through. So in this case, I took a little bit of air, and I passed some light through it, and I asked, how much light came through? So if all the light passed through, if none of it interacted with the molecules in the air, you would see a line right up here. right? 100%. But what you see actually is some interesting hair or fuzz. So there's a little bit over here, there's a peak sort of in the middle, and then there's a peak out on the far end. And what you're seeing is places where the energy of the light has been absorbed by molecules in the atmosphere. In this case, it's water that's absorbing some light. In this case, carbon dioxide. And in the far case, water again. So we're actually seeing what molecules are in the air, and not only that, but how many of them are in the air by looking in this different region of the spectrum, by looking with different eyes. So this is what the air looked like before we did our experiment. What about after? We breathed out. So I did this experiment. I breathed into the instrument that did these measurements, and here's what happened, right? Certainly different. Very different, right? There's much more water, much more carbon dioxide, much more water here. Maybe not surprising. I mean, that's kind of the way you would think of it. Thank you very much for the laser pointer. We'll actually be able to see again. So much more of all of these things. But there's more of what was already there. There's not anything new. And that's why I said what you did was a little bit boring. Because when the Earth breathes, as it does through volcanoes, it breathes out about the same thing that you do. Carbon dioxide and water. So you are doing something that was going to happen anyway. And from the perspective of looking for life, that's kind of boring. And I have to tell you, actually, I worked really hard to make this interesting because I knew this would be the main result. So right before I did this experiment, I took a couple of cloves of raw garlic and I crunched them up, right? And then right away, I breathed into the spectrometer. And I was really hoping that I would see those garlic odor molecules show up in the spectrum. And I have to tell you, for 3 hours afterwards, even those of you in the back of the room would have known what I did. But it didn't show up here, right? And it makes the point, we are looking for signals that are big and bold and a major change. So what is it that we're looking for? I mean, if what we just did is boring and ineffective from the standpoint of looking for life, what are we looking for? And in the most general terms I can offer, we need things that we can see, right? Meaning it needs to be a planet-scale change that happens at the surface and affects the light that's reflected either off the surface or through the atmosphere. It needs to be something big. And it needs to be something that we can't explain by any process or means other than biology, right? We have to exhaust all other possible explanations for what we see. In the case of the Earth, the CO2, the carbon dioxide, and the water that we breathed out can also be made by volcanoes and other stuff, right? There's easily another explanation for it. We're looking for something that could not exist or we can't explain otherwise. And that's a tall order, because we're asking to understand planets that are occurring, processes that are occurring on planets that we really don't know very much about. And this is where it becomes important for the geochemists and the geophysicists and the atmospheric chemists all to become involved in this problem and understand the system as a whole. So what is it that makes Earth look unique relative to its peers in the solar system? If you look at Venus, and this is exactly the same kind of graph, right? So here's wavelength here, and here's the amount of light that's absorbed. So if you look at Venus, Venus has a very thick atmosphere of carbon dioxide, and some of the light in that part of the spectrum is pulled out by CO2. So we see the CO2. We look at Mars, it's the same thing, but those are both frankly boring for exactly the reason that I said what you did was boring. Earth has that same boring aspect, but this is interesting, right? This, for those of you who can't see in the back, is ozone, and ozone comes from oxygen. It is what makes Earth look unique from a distance. And how did it get here? Right? We sort of take for granted that we have an atmosphere filled with oxygen, but we didn't always. Earth started out as a planet with no oxygen and spent that way for about 2 billion years or so. We have these to thank. So we think of oxygen as coming from photosynthesis, which comes from plants, right? But the plants learned how to do it from these cyanobacteria that predated them by 1.5 billion years or so. These are tiny little microorganisms. Can't see them with the naked eye. But Louis Pasteur, the French microbiologist who knew a thing or two about the capabilities of microbes, said, "The power of the infinitesimal can be infinite." You could fit 1 trillion of these things in the palm of your hand. That's how small they are. But over geologic time, they took a planet with no oxygen and they filled the atmosphere to the 20% oxygen that it now has. Right? That's what we are looking for. We have a very difficult time explaining the presence of that oxygen on our Earth in any other way, and there's enough of it there that we could see it from light years away if we looked with the right kind of eyes. That's actually the reason for the whole concept of the habitable zone, just to come back to that point. Remember I said the habitable zone is not meant to exclude the possibility for life in places like Europa or whatever else. It's meant to say where could water be liquid at the surface? And this is the reason. If you want to do photosynthesis, if you think that photosynthesis is the only way to get this planet-scale signature that's really difficult to obtain any other way or explain any other way, you need two things. You need sunlight and you need water. And those things have to coexist at the surface. That's why we have the concept of the habitable zone. That's what its purpose is. It's not to say where could life be possible. It's to say where could we have a chance of finding it. So let's actually talk a little bit more about oxygen, because oxygen turns out to be pretty instructive. And there are three questions that I want to ask. A lot of the focus gets placed on oxygen, and so I want to talk a little bit about it. And the first is oxygen an obligate product of photosynthesis? If you have photosynthesis emerge, does it always make oxygen? So the first answer is easy. No. Right? Here's a picture of two things. So these green guys are the cyanobacteria that we just talked about. They're green because they have chlorophyll, and they do oxygen-producing photosynthesis. And cozied up right next to them, these tiny little purple things, they photosynthesize, but they don't make oxygen. Right? There are actually several kinds of photosynthesis that don't make oxygen at all. And this one, biochemically, is quite a lot simpler than this one. And in evolutionary terms, it predated. So this non-oxygen producing photosynthesis predated oxygen producing photosynthesis by maybe 1 billion years or so. So if you think about our planet, for about half the history of life on Earth, which dates back maybe 3.8 billion years or so ago, we had life. We even had photosynthetic life, but we had no oxygen that could be detected from far away. So that's one of the key problems facing us now, and even in my research group, is what other signatures of life are there? What else does life make that can be seen on the surface or makes its way into the atmosphere? And how does the planet process those things? What form do they ultimately take, and what would we see if we looked at a telescope? Is oxygen a unique product of biology? Is it a uniquely biogenic signature? And the bad news is it's not. Actually, there are at least 4 different ways identified, 4 different processes that will fill a planet's atmosphere with oxygen. Right? If we look in the air around us, there's water, H2O, carbon dioxide, CO2. There's oxygen there, right, locked up in molecules. And if there's a way to free it, like, for example, if a photon from the sun bangs into it really hard and breaks it apart, you actually can get oxygen, right? And we need to look no further than our next-door neighbor. There's actually oxygen there on Mars. Not a lot, but a little, and there surely isn't photosynthetic life at the surface. So we actually have an example of a place where processes like this are happening, and it can give us these false positives, these red herrings, as we search for life. So the good news is that if we understand the context, so if we understand something about the kind of star it is and what its light field looks like, if we understand how the planet operates, at least as much as we can say, and we look for other molecules, things in conjunction with oxygen, like carbon monoxide or methane or other molecules, we can have some clues as to the source, right? If we looked at oxygen on a planet like Earth, knowing what we know about the sun and the geologic context, we could say that must come from life. Right? And if we look on other places, we have the potential to use these other things, other molecules, other bits of context, to also say, is that oxygen unique to life? So lastly, is oxygen emblematic of our being unimaginative or parochial in the way we think about life? Does anyone know what that is, out of curiosity? It's the horta, right? The horta comes from the original Star Trek, and it was a creature made out of silicon, right? This idea that life could be made out of something very different sticks like a splinter in the mind. I don't think I've ever given a public talk where this question didn't come up at the end of it. So I was part of a panel discussion once, actually, about 5 years or so ago, public panel discussion, and it was 3 proper astronomers and me. And they had arrayed us kind of from the most here and now to the most sort of, out in the future kind of science. So I was sitting down at the far end. And we did our discussion, and a question came from the audience about, could life be made of something very different? And actually, it was phrased in kind of an out there sort of way. And this question comes, and the 3 astronomers, in perfect unison, I mean, as if they had rehearsed it, all went, Tori. So this is my niche, apparently, right? I'm the left fielder of the exoplanet community. But people are interested, I understand. And actually, Carl Sagan summed up the problem really nicely, as he often did. He said, there's a famous book published about 1912 by Lawrence J. Henderson, in which Henderson concludes that life necessarily must be based on carbon and water and have its higher forms metabolizing free oxygen. I personally find this conclusion suspect, if only because Lawrence Henderson was made of carbon and water and metabolized free oxygen. Henderson had a vested interest. So, but is it possible? Could life be made of something else? So the truthful but unsatisfying answer is that from the standpoint of exoplanets, it actually doesn't matter all that much. It matters a little, but remember that what we're looking at when we look for evidence of life is not going to be the life itself. It's not going to be the molecules of which the thing is made. It's going to be what the thing does, right? Does it make oxygen, or does it spit out carbon dioxide or something like that? It doesn't matter so much what it's made of. It actually matters more to think about what the life is made of and what its requirements are, to know where to point your telescope in the first place. And I guarantee you that if we have, if we look out our sort of 10 parsecs or so and we have several dozen worlds that we could point our telescope at, we're going to go for the ones where we know have conditions that are suitable for life originating. We're going to go for the ones that we know have water, that we know have carbon, because that's where we know life can survive. But I understand that's an unsatisfying answer, and people want to know about this. So there actually has been some serious scientific thought dedicated toward this, and there was a National Research Council study convened around this. Actually, a number of very prominent scientists participated in this, and they addressed themselves to this question. If we think as broadly as we possibly can, what could life be made of? And they published a report, which you can download, right? If you're fascinated by this topic and you want to read 150 pages about it, you can go and download that. It's easy to find on the web. But I'll summarize for you what they said. They said, if you think as broadly as you can, really, the only absolute requirement for life is energy. Everything we understand about physics and chemistry dictates that life requires a source of energy. It's probably made of carbon. So they made the point, they think it's carbon. And actually, Carl Sagan kind of said that he thought of himself as a carbon chauvinist, despite the statement that I just made, and not so much a water chauvinist. And actually, that's a reasonably consistent viewpoint. So this is how I would have looked at it as well a handful of years ago if asked that question. And they said it requires a liquid, but they went out of their way to say that there's no fundamental reason that liquid has to be water. So this was the summary viewpoint of this group of people, is that life probably is made of carbon, probably doesn't need to have water, really could be any liquid at all. And we have examples even in our own solar system of other places where there are liquids other than water. Saturn's moon Titan is covered by seas of liquid methane and ethane, right? And according to this report, yeah, sure, it's possible. Here's my own 2 cents. I tried to think about this like a chemist, right? And I have to say, as a person who likes to believe that he has some imagination, I really would love to find an example of life that is very, very different from our own, that's based on some fundamental difference in the chemical principles of how it operates. But my own 2 cents, when I think about it as a chemist, is that it's not just a liquid we need, it's a solvent that we need. And a solvent dissolves things and it mediates their interactions. And for a number of reasons that fill their own 1-hour lecture, I actually think that the properties of water, or something very like water, are critical to the interactions that confer lifelike chemistry. So I actually have become a water chauvinist where I was not before. I think that water is important. And because that solvent mediates the chemistry of life, it kind of constrains what else life could be made of. So I have a colleague who went through the exercise of showing, in principle, that silicon, which is everyone's favorite sort of second choice, can make a lot of the molecular forms that carbon can. However, if you put any of that chemistry in liquid water, it either spontaneously combusts or explodes. Right? So it matters very much what the solvent is, and those things put together, to me, suggest that water still is the place to be looking. So if we do our job, if we build the right kind of telescopes, if we find the right places to look, someday we may see something like this. This is one of these light spectra, again, wavelength on this axis, only it looks different than what I showed you before, and it looks cluttered and ugly, right? There are all these error bars, which are a measure of how uncertain those measurements are, right? And we could sort of see some waviness in there, but nothing like the sharp peaks I showed you before, right? So this is what we can hope to get, and actually we can directly improve that picture if we invest in bigger telescopes. We actually can resolve that picture better. We can collect more photons, have more certainty in our measurements. So those are choices that we'll have to make. We'll have to decide what wavelengths do we look in, right? What molecules do we really care about seeing as evidence of life? And how big a telescope do we build? Because the bigger the telescope, the farther out we can look, and the more worlds we'll have a chance of investigating for life. So these are the choices that lie ahead of us as we think about looking for life. And just to wrap this up, this is a Hubble ultra deep field image. So Hubble stared at a tiny little patch of sky for a long time, and everything that you see in this picture is a galaxy. Every little bit of light that you see in that picture is a galaxy. There are 70 billion trillion stars in the observable universe. And we know that life has originated around one of them. We don't know whether life has originated around any others. And there are people working very actively on this question: how frequently does life emerge, given the right set of conditions? It's one of the hardest problems in science. And we actually now have the potential to bring observational evidence to bear on that question by looking around us, finding the right set of conditions, and asking, is life there? So, thank you very much for your attention. I hope this was fun and interesting. I'll be happy to take any questions.
So you showed the two plots, the one very crisp plot of Earth, which showed ozone, carbon dioxide, and water. Why was there no oxygen peak in the really crisp plot that you showed earlier in the talk? And do you expect to see it in the less well-resolved plots from a much further distance?
Yeah, so that's a great question. It partly depends where in the wavelength range you are looking, because the same molecule will interact differently with different wavelengths of light. And one of the reasons is, so part of why the absorption of light happens is that you can imagine a molecule as let's say, two atoms on a spring connected. And when they absorb energy, what happens is that they start to vibrate, so that's where the energy goes into. That process happens much more effectively if the two atoms differ in their charge. So if one is a little bit negative and one is a little bit positive, right, that creates a dipole that allows them to absorb that energy and do this sort of thing. So it's actually hard to see oxygen across a lot of the spectrum because it lacks that dipole in exactly that way. Ozone is much easier to see.
And do we expect to see ozone where oxygen has been produced?
Yes, we do. We do, for the same reasons of photochemistry that we get ozone in our own atmosphere.
Okay, on an Earth-sized planet, ultraviolet light can break up water molecules into oxygen and hydrogen, with the hydrogen light enough to escape the gravity of the planet over a long period of time, millions and billions of years. So how do you tell oxygen produced in this non-biological way from oxygen produced organically?
Yeah, that's a great question. And actually, it's a little bit easier to answer that question with the other main way that you get oxygen. So I remember I said that we have O in the water around us, but we also have O in the CO2 around us, right? So a lot of what we see on Mars, for example, the oxygen that we see in the atmosphere comes from that same process you described, the ultraviolet breaking of the molecule into carbon monoxide and oxygen. And so if you see a lot of carbon monoxide around, as an example, that would be a telltale sign that this process has been going on. So what you do in order to understand the process is look for its residuals. So the great thing about chemistry and physics is that they work the same way everywhere, right, as long as you understand the environment well enough. So if you understand the process and how it works and can look for telltale residuals of it, like the carbon monoxide, for example, then you have a potential handle.
I'm a physicist and electrical engineer, but I'm also a cynic. Could you tell us what is the total budget, that's everyone involved in this project? And once you've told us that, tell us whether you think the homeless guy in San Jose cares two hoots whether you have discovered life compared to his life here.
Yeah, I think that's an important question for us all to ask ourselves. You know, the total budget for the science going forward, at the moment is not very much, because what we're doing is trying to create the science context around what we will do if we decide that that's an important enough question to address. I think that one of the things that makes us who we are as people and as a species is our curiosity about what lies beyond. And I think that it's worth pursuing questions just for the sake of that fundamental knowledge. That's my personal view on it, and not everyone shares it. Absolutely, there are differences in the way that we prioritize our spending, and I think it's important for all of us to consider that. So I think it's a good question and one that's important to have raised.
When will that Sunshade project take off?
So actually, the thing, you know, you can always see videos and think, well, that looks nice, you know, in the little animation, but when is it actually going to happen? So actually, there is a scale model built at JPL, the Jet Propulsion Lab, out of flight-qualified materials and to flight specifications. So they know that they can make it, and they know that it can operate. When it actually happens, I think it's still a ways off. And typically the way these things work is that there will be smaller scale kind of technology demonstrations. But I know that there is an operable scale model that actually exists now. And I think that's as much as I personally know about it.
Thank you for a good talk. I was wondering two things. I hear you're involved with the Europa mission. I heard that the Galileo mission had some problems with radiation at Jupiter environment. Is there any concern about how the mission might have to change at Europa? That's one question I have. Mm-hmm. And the other is about the Webb Infrared Space Telescope. And I was wondering about plans in that to use light from covering up the star from a transitive star to look for signatures of molecules in the spectrum.
Yeah, two very good questions. So first, the Europa one. Yes, there is a very intense radiation environment at Jupiter. It's very high energy electron radiation that wreaks havoc with electronics and even things like glass in optics and stuff like that. What's fortunate is that we understand that radiation environment really quite well, and the mission is designed around it. And you heard Andy refer to it as a multiple flyby mission. So instead of putting something in orbit and just going around and around and around, it actually orbits Jupiter and just makes these very brief passes by Europa. And that's by design, because it spends very little time at Europa. It's going fast, and it moves off to somewhere else in the orbit. So the first and best way that you deal with the radiation is to not spend very much time in it. And then you find ways to shield, and you build with components that you know are radiation hard. So the second question about the Webb telescope, actually, I stocked myself with all kinds of extra stuff here. So James Webb Space Telescope is a telescope that will launch in about 2 years, fingers crossed, hopefully. Just for scale, so the one all the way over on the far left is Hubble, which is about this size or so. Webb is much bigger, much bigger. and will collect a lot more light, have a lot of capabilities. And the question was, will we actually be able to do some of this work of investigating the chemistry of the atmospheres by looking when the planet passes in front of its star? So if you imagine there's a little ring of atmosphere around it, as it moves in front of the star, you get a little bit of light shining through, and you see that change the spectrum of the star. Absolutely. That's part of what people are looking forward to with the Webb Space Telescope. I think will do that pretty well to objects down to the size of maybe a few Earth radii or so, probably not to the Earth-sized planets that we're most interested in. That will have to wait on a bigger, more capable telescope.
Thank you.
You showed a chart with something around 1,918 exoplanets on it.
Yes.
Are they all from the stars in the Milky Way, or have we ever detected a planet outside of our galaxy?
Yeah, so maybe I actually have a slide for that too. Let's see. So this is where, so most of those are from Kepler, right? More than half of what we've seen are from Kepler. This is where Kepler actually looks. So the sun is in this little spot over here. And Kepler's field of view is quite narrow, actually. It just looks at a relatively small patch of sky and out about 3,000 light years or so. So everything we know from Kepler comes within this one little patch of this particular arm of the Milky Way. That's true for many of the other methods too. There is one method that I don't understand very well. It's called gravitational lensing, that for which distance actually doesn't matter all that much. I don't think it's discovered anything outside our galaxy so far. So I think we really are limited to light that we can see as an individual star and not light that we can see as part of a bigger galaxy. So I think we're sort of still thinking locally.
Thank you for your talk, and I applaud your ambitions for the Europa mission. So my question is two-pronged. One, what is our most optimistic scenario with Europa? And secondly, speaking of optimism, my generation is hugely optimistic about the future of space exploration, be that in our solar system or outward. However, we have a much older generation in charge of the Congress and the budget. So how do we galvanize the masses or the senators and congressmen to share that sense of awe and curiosity that I assume most of us in this room have?
Yeah, so two questions. Europa is popular tonight. So the most optimistic scenario for Europa, the multiple flyby mission is designed to assess Europa's habitability, not specifically to look for life. And it will be an extraordinarily capable mission. For me, one of the biggest unresolved things about the habitability of Europa, so there's very good evidence that there's a huge ocean of salty water beneath the surface of Europa. One of the most unresolved problems from my perspective is whether there's any energy that gets in there to be used for life. And that really depends on whether that surface ice overturns into the ocean or not. And this mission, I think, really will help us resolve that. So we will be able to see the structure of the ice. We'll be able to see with radar the boundary between the ice sheet and the ocean beneath. We will have a very good handle on the chemistry that exists at the surface. And if any of that is a product of the ocean having come up and splashed out on the surface, we'll characterize that quite well. So best case, most optimistic scenario, we will learn a great deal about the habitability of Europa and a great deal about its sort of geophysics besides. And maybe we will find some molecules that are tantalizing and motivate further study. As to the question of galvanizing support around stuff like this, I was having a conversation with Andy right before the talk. So he and some colleagues wrote a textbook in astrobiology and sort of dealing with space sciences about a decade or so ago. And we've been revising it just these last few months. The amount that's happened in that time is extraordinary. That's when Cassini has visited Saturn. That's when most of the exoplanets now known have become known. That's when we've done most of our driving on the surface of Mars and the mapping of it and all the stuff that I described. So I actually think that quite a lot has happened, and I feel fortunate that there's as much support as there is. I think this topic in particular, exoplanets, has such a great sense of potential, at least, and there's such excitement within the community that if we can find the right venues to just share that excitement, not even sort of packaged and marketed excitement, but just legitimate excitement, I think that's motivation to go and look.
Okay, so you mentioned gravitational lensing for a moment there, which is like really out there method for detecting exoplanets and has detected planets that aren't even orbiting stars. Is there any similar idea with methodologies that don't include spectrographic data to detect life around other planets? Is there anything that you're aware of that's really out there method for doing that?
Well, so in what I've discussed, I haven't discussed SETI at all, of course. So that's, I think of myself as a settle person. I would be happy to find life, no less intelligent life, so that's just settle. Exclusive of SETI, is there a way to do this that is not spectroscopic? So what we get from the star, we will not in any of our lifetimes actually physically go and sample. Right? Voyager 1, which is now the most distant object from the sun, left Earth when I was in first grade or something like that, which is longer ago than I'd care to admit. To get to the nearest star to us will take another 80,000 years, moving at its current 30,000 miles an hour or so. So we will not physically go there, barring some amazing thing. What we get to use as our evidence is light. And what we can say with light, we can say best when we break it apart Pink Floyd style and see how it has interacted with matter on its path of travel from the star to the planet to us. So I don't, perhaps it's a failure of my imagination, I don't see a way to do it other than that because what we get to deal with is light.
Maybe we'll figure it out with neutrinos or something, I don't know.
Maybe.
Throwing it out there.
So my question was, why doesn't NASA work with different countries regarding space exploration, as there's China, India, Russia, maybe even France working on missions on Mars, Europa. So if we combine the budgets of all those nations, we might be able to fund more things?
Yeah, that's a good question. So I'm not a policymaker for NASA, and I don't speak in an official way for NASA. I can say that there are many examples of that sort of cooperation. So, for example, the Curiosity rover has several instruments that are contributed from other nations. There are examples the other way around, where missions sent, for example, by ESA or JAXA or other international space agencies have involved instruments built by U.S. scientists or involve those scientists in one way or another. So there certainly are examples of that sort of cooperation and collaboration, even at the mission level. And I agree, this is sort of a human scale endeavor, not a national scale endeavor. And I think it's important to think about how to make that happen.
Three more questions.
Okay, 3 more questions.
Talking about methane, I believe you mentioned earlier that would be one of the gases that you would be looking for. Methane is a very volatile gas, of course, and needs to be reproduced constantly. So methane has been found in the Martian atmosphere, but the Curiosity rover has not been able to detect any methane on the ground. Is there an explanation for that?
Well, so Curiosity has seen some very low levels of methane with occasional spikes as it goes along. So there are 2 observations here. One is there are telescopic observations that said there's methane in the atmosphere of Mars, and those have been debated for a long time. So there are things you can point to that suggest maybe those aren't real, and people have been looking forward to Curiosity to answer that question. It looks like Curiosity has seen some low levels of methane with these spikes, but the question actually raises an important point. So people used to, less than a decade ago, used to say, if you saw oxygen and something like methane together, that's an absolute smoking gun for life. Can't happen any other way. We see oxygen and methane together on Mars. It's really a question of degree, because as you said, those two things tend to combine and react with one another, so one or the other will hold sway, but not both. And if you see them both in abundance, it means that there's a mechanism for making each of them sufficiently rapidly that they actually rise to a detectable level. And that, one of the hallmarks of life is that it does things much more rapidly than would happen in the absence of life. So that's something that you would look at and say, that's awfully hard to explain any other way.
So why you emphasized search the habitat planet or stars like Earth-sized, not like something bigger sized or smaller sized? Another question is, when NASA will send the mission to Europa? By what year, what time?
Yeah, I'll answer the second one first. If things go as we hope they will go and as they were planned to go, it would happen in the early 2020s, which in terms of instrument and mission development timescales is frighteningly close, actually. So fingers crossed that happens. As to the second one, that's a great question, actually. How does planetary size affect things? And I think the honest truth is that if we are presented with a range of options from which to choose, and there's a choice that looks a lot like Earth, we always will go for that choice because it's what we understand the best. But that doesn't mean that people haven't thought about your question and tried to provide the scientific context around it. So a lot of people think, for example, that having a way of recycling the planet's crust, like we have on Earth with plate tectonics, might matter a lot. We know that can operate on Earth, on a planet of our size. How would it operate on a planet with twice that size and 8 times that mass? Do the geophysics work the same way? There was a paper, 2 papers that came out around the same time, and one said, of course it works, and the other said, of course it doesn't, and it's things that people are debating. If the planet is too small, does it run out of the internal energy to keep that process going? And one of the things that's really weird, so remember there are these sort of 2 bars on the bar graph for planets for which we have no comparable example in our solar system. We have either small rocky planets that are made out of metal and rock, or we have the big gas giants that are predominantly ice and gas and so forth, but nothing in the middle. And we have no idea how things would work on these planets, except that we know that physics will work the same way everywhere, and we can at least try to model and predict. And what becomes very interesting is when you look at the densities of some of those things. So the density of our planet reflects a mix of iron basically and rock. The density of Saturn reflects a composition primarily of gas. For these things, you get densities quite in between, that look like maybe some of them are mostly made of water. A small rocky core and thousands of kilometers of water. How would a world like that work? Right, at the pressure of the bottom of an ocean that's thousands of kilometers deep, water at any temperature actually becomes a solid, and that changes the dynamics a lot. So it's a great question, and all I can say is that people are actively pondering it, and we hope that context will be there when we actually have a choice to make. Last question.
Could there have been life on Mars sometime in the far distant past?
Well, so that's also a question that we're trying very hard to answer. We have the great thing about Mars is that it's because it's our next door neighbor, we have been able to send a cadence of spacecraft there every 26 months or so, and it's allowed us to design a program that works its way successively toward answering that question. So up to the present, with the Curiosity rover, we've been trying to address the question, was Mars habitable in the past, or is it now? And the answer to that question seems to be yes. It seems to have been an environment that supported liquid water at the surface in its past. It may be an environment that supports liquid water in its subsurface, at the present. Could life have evolved there or originated there? Those are the conditions that we feel are suitable for life, and we have an example here on our own Earth of life having originated under such conditions. How frequently life arises when the conditions are right, we really don't know. And so there's another chance, just like with the exoplanets, to bring observational evidence to bear on that. And there is the potential, at least within the next decade maybe, to do the sort of science on Mars or on samples returned from Mars that would actually help us address that question. All right.
Thank Dr. Hoehler.